new Ophir StarBright is the most advanced of Ophir's family of handheld laser meters. It supports all standard Ophir sensors for measuring average power, single shot, as well as repetitive pulse energy and frequency, power, position, and size of your laser beam, irradiance and dosage of UV and visible LEDs. It has a large, brightly lit color display for enhanced visibility, and the navigation panel and soft key controls make it easy to use. It has a USB flash disk interface for onboard logging of data, as well as USB and RS-232 connectivity to a PC. Logged data files can be uploaded to the PC, or the StarBright can be operated while connected to the PC. StarBright works with the Ophir StarLab laser measurement software and StarCom data logging software. A LabVIEW driver and COM object make it easy for developers to integrate laser beam measurements into external systems. It's regarding the user experience that StarBright really shines. We've done this in two areas: ease of basic use and advanced use. Let's walk through the various functions. First, we'll turn on the meter with no sensor attached. After initializing, we come to the settings screen. Here we can see the baud rate for RS-232 communication, full-scale voltage value for the analog output, display language, line frequency, 50 or 60 Hertz according to the setting in your country, color scheme, for example, to get maximum contrast when using various safety goggles, and time and date. Note the short explanation text for each setting. We can also zero the instrument, which we recommend to do periodically, every other month or so, to zero out electrical biases that sometimes build up. Let's begin with basic measurements. Then we'll move on to graphical display options, more advanced functions, and data logging. We'll now connect a thermal sensor used for measuring average power as well as single-shot pulse energy. Note how the StarBright automatically restarts as it reads the sensor's calibration and related data stored in the sensor's EEPROM. Here, we set the basic parameters of our measurement. The available settings are defined according to the specific type of sensor. Those definitions are part of the related data programmed into the sensor. Average power or single-shot energy. We'll start with power. Range, auto-ranging or manual ranges. Again, which ranges are offered depends on the sensor. Wavelength. Average. This displays a running average of the readings over the selected time rather than the actual real-time reading. This is useful when trying to measure an unstable beam. Offset, for canceling out unwanted background light. Now let's set it to measure energy. A thermal sensor is too physically slow to measure energy per pulse in a repetitively pulsed beam. We use other sensors for that. But it can measure energy of a single pulse, when there will be at least a few seconds before another pulse arrives. The ready indicator means the sensor is now ready for another pulse. Range. Note that there's no auto-ranging in energy mode. Wavelength. Threshold. You can select from 3 different trigger levels below which the sensor will ignore pulses. This is useful if the environment is thermally noisy and you want to avoid false triggering. We'll now switch to a photodiode sensor used for measuring low average powers. We again set the sensor parameters, and we'll just highlight items that are different than what we've seen already. Range, note the dBm option, relevant in telecom and similar fiber applications at the sort of low powers for which these sensors are commonly used. Wavelength, because their spectral response is not flat, these sensors are calibrated with a full spectral curve covering their defined spectral range. The drop-down wavelength window displays a number of default favorite wavelengths you can choose from. If the wavelength you need is not one of the displayed favorites, you can select any of the favorites or none, then click on Modify and change the currently selected wavelength to any other wavelength in the specified range. After all wavelengths in the range are in there. You can use this to set up a favorite wavelengths list to suit your needs. Any changes made here are automatically saved to the sensor's memory, so they'll move with the sensor if you change instruments. Filter in-out for sensors such as this one that have a removable attenuating filter. We'll now connect a pyroelectric sensor used for measuring energy per pulse of a repetitively pulsed beam. For the most accurate reading when using a pyroelectric sensor with any Ophir meter, we recommend that you perform zeroing with the meter and the specific sensor connected. Once done, you won't need to do that again for this sensor as long as it's being used with the same meter type, in this case a StarBright. When you change meter types, you'll want to re-zero the sensor. Here we set energy or power. For any beam whose energy per pulse the pyro sensor can measure, it can also measure the beam's average power. Exposure measures the total accumulated energy over the set measurement time. Range, note again that there's no auto-ranging option for energy measurements. Wavelength, depending on the type of absorber used in your sensor, such as the metallic or the broadband BF or BB absorbers, there might be just a few discrete wavelength settings or a full curve with the option to modify. Pulse length. This sets the maximum pulse length, the time window during which a given pulse is integrated, held, and measured. Choosing a given maximum pulse length setting determines, of course, the maximum pulse repetition rate, as can be seen in the specifications. Ophir's Pyro-C line of energy sensors gives you up to 5 different pulse length settings to choose from, so you won't fall between the cracks by having a pulse length too long for the one setting, but a repetition rate too high for the other setting. Diffuser. If your sensor is one of the models having a removable diffuser, here's where you tell the StarBright whether the diffuser is now in or out. Threshold. These sensors have a user-adjustable minimum threshold, so you can operate even in noisy environments by setting the threshold to just the right level to allow your pulses in while keeping noise out. Average is, as we saw earlier, to display a running average of readings over a selected time period to enable measuring unstable beams. When we measure energy, we're shown the pulse energy as well as the repetition rate. In power mode, we're shown the average power of this same beam. In exposure mode, we can measure exposure from when we press start to when we press stop. Alternatively, we can preset the time or the total number of pulses over which we want the exposure measured. We'll now connect a beam track sensor. Beam track is a family of sensors that measure power as well as position of the beam centroid, and for most of the models also beam size, all at the same time. Most settings have the same meaning as they do for other sensors. Note how the XY position of the beam is displayed, as is the beam size when the beam is within a specified distance from the center. A schematic graphical representation is shown as well. A useful feature of the StarBright is that you can zero the axes of the position display so that the beam's present position becomes the 0 point. The X and Y coordinates are now referred to as the X and Y offsets. Graphical display options. A range of display formats is available. By clicking Menu Display, you can choose the standard digital readout with bar graph display that we just saw as default. You can also choose a changing bar graph where the color changes depending on the reading's percentage of full scale. You can select analog needle with the option of using persist to see the recent history of where the needle has been, or zoom to zoom in on the area of the reading. You can use a line graph to graph laser output as a function of time, especially useful, for example, for fine-tuning laser power. You can adjust the value of the y-axis and the horizontal sweep time to what's most convenient for you. Reset zeros the graph. You can have the screen display real-time statistics for the current measurement. You can set pass-fail criteria to give a warning when the measured value goes above or below your preset limits. When you need to do more than just measure, StarBright offers a range of functions for more advanced processing of readings. Average, we saw earlier. Fixed offset subtracts a preset value that you define from all subsequent readings. Scale factor is a factor by which all subsequent readings will be multiplied. For example, when you're measuring after a known beam splitter, but you want to display the calculated value before the beam splitter. Reference allows you to normalize readings to a reference value. For example, you might measure the power coming out of the laser and then display all subsequent measurements, say at various points along the rest of your optical setup, as a unitless ratio relative to the reference value. Density displays the readings in units of power or energy per unit area. You're prompted to enter the beam size in either one dimension if it's a circle or 2 dimensions if it's rectangular. You can also combine functions. Here we can see that we're applying averaging and we're in density mode. When we navigate off to the right of the screen, we see the details of a scale factor and a fixed offset that have also been applied. Logging. To log data on board the StarBright, we insert a USB flash drive in the slot and then simply go to the log function in the menu. We can later access the file storage and we can upload the stored data to a PC running the Ophir StarLab software application. For all its advanced capabilities, StarBright is a very intuitive instrument, and you likely will not need to check the user guide much. Still, if you have any questions, please feel free to contact us either directly or via your local Ophir representative.